Okay, so I will be speaking about the non-radiative dynamics, non-radiative relaxation. So I have a screenshot of the script here, but like the sort of files that you will need to run this script are the energy pop, oscillator strength, input overlap, and then your RRR file that you are generated from the previous step. So here is where you impute the initial conditions. I usually would just look through the ones that have the highest oscillator strength and um, choose that. And here it's clear that this file needs the energy pop files and the RRR. And here is where you specify your O min and O max for your structure. So what the results look like, first of all, you would get something like this, which specifies the frequency. I'm not very sure of what this frequency is. I know it's supposed to be like an angular frequency thing, but I am not I don't exactly know what it is or like where it's coming from. And then you would also get like rate constants, I believe, for the electron and the hole. And for this is from one of my structures that I had, and here is where like the excitation started, and it's sort of like diminished, the intensity diminished before getting to the homolume. So that's all.
Okay, please join in thanking Laura. So any questions, suggestions, or constructive criticism?
Yes, can somebody please explain this frequency?
Maybe would you like to try?
I'm not sure what that frequency was. I was just testing to see if I could get that to output as well.
Okay.
I'm not sure what that one is.
Okay, let's ask London, are you connected? Are you online?
I am still here, yes.
Okay, would you please teach us what is frequency, how it is related to your presentation? Maybe if Lola stops sharing, London starts sharing, and you can show which part of equation this frequency corresponds. It's also shown here.
That?
Yes.
Okay, so that's not what I thought it was then.
Lola, are you satisfied or you need more explanation?
What'd you say?
I'm asking Lola this.
Lola and I are sitting at the same table right now. So we're also talking to each other.
I wasn't aware of this. I'm just looking for confirmation of Lola if she's satisfied with the answer.
Yes, I am.
Oh, okay. So the dynamics that we observe is a superposition of several eigen frequencies. And maybe London, if you stop and Lola restarts sharing her, and the rates KE and KH that we were discussing with Amara and that Lola is showing here, those combine all eigenrates that come from solution of eigenvalues, and depending on the initial conditions, this KE and KH will be different because combination of eigenstates for each initial condition will be different. This rates of relaxation is something that can be compared to experiment. It is one of the practical research. So, like if, for example, if I don't care about theory and just want to quickly compose something that can be of interest to experimentalists or to the editor of a journal, I can just systematically scan different initial conditions, find this KE and KH as functional initial condition, and discuss what this result is. So it's a minimalistic practical research that can be done with this tool. You see response of the relaxation rate to initial excitation. Other questions, additional questions to Lola, or maybe question of Lola to herself or to everyone?
Could you go to your second slide? So I noticed there's a temperature variable that's set at 77 Kelvin, and then in the default file there's a temperature of 1 Kelvin. Does that matter? Do we have to worry about varying that too much?
No, you don't have to worry about that. I mean, I don't think you don't have to change.
Yep, okay.
Thank you, Hadassah. It's all same as Joseph. You are coming to the point. You are immediately finding the biggest places of the code. So may I ask Lola to stop sharing, London to start sharing, and go to one of because there are some important illustrative materials. Yes, write this slide. So the upper left. Yeah, maybe if you make your slides in presentation mode.
Yes, I'm sorry. I accidentally opened WebEx also, and that was getting in my way. There.
So this is RE. So it is a part of the Redfield tensor that is responsible for.
Oh, wait a minute. Sorry, this is you. This one is RE.
Okay. Who cares?
Yeah.
Yeah, please go to presentation slide so that we can see it a little bigger. Yeah. So first, it is segment. It is not the whole triple R matrix, but only a fragment that relates to pairs of orbitals in the conduction band. Second, if you look on the triple R matrix, you will see that it is large near the diagonal, zero away from diagonal, but it is symmetric in respect to the diagonal. Here, the illustration that London is making follows this pattern on the upper diagonal. So it's a substantial number on the first upper subdiagonal, and then it is zeros in the lower half of the matrix. So this upper and lower halves of the matrix correspond to thermally induced relaxation and thermally induced excitation. Like if the path is high enough, it may promote electronic states from lower energies to higher energies. And this detailed balance mechanism would depend on the temperature. If it is programmed properly, the lower half of the matrix will be non-zero. But for technical reasons, to avoid numerical instabilities that Joseph observed while exciting it too high or too low, so to avoid these numerical instabilities, this part of the theory, this part of the code is simplified and postponed. So technically, the code is hybrid of couplings computed for real temperature. When we do molecular dynamics, we set up temperature, right? And it is our way to control them. The higher the temperature, the quicker the relaxation. But second part, there's the lower part of the matrix that one is showing should be non-zero, and it should be controlled by Boltzmann function. Here it is skipped because it creates more problems than solutions. But your question about setting up an explicit parameter for the temperature, if added, if the code is developed further, would affect lower part of this RE matrix.
Yep.
Yeah, thank you for critical item. London, thank you for sharing. You can stop sharing. Let's check if there are more questions to Lola. If there are, we ask her to share. If there are no, we go to the next speaker. So more questions to Lola once, more questions to Lola two, more questions to Lola three. Okay, good journey. Thank you, Lola once again.